Today you will find and interpret z-scores and use the empirical rule to answer questions. Standardizing shifts and rescales data using the mean and the standard deviation. It shows us to use the standard deviations to measure unusualness. Okay, so I can compare individuals to a group, or I can compare values with unlike scales or units. For example, if I wanted to know if my ACT was better than my SAT, I can standardize my scores to see which one is really the better of the two. We call this standardizing, or z-scores. Values with no units. It measures the distance from the mean or the center of a distribution. If my z-score is positive, that means I am so many standard deviations above the mean. If it is negative, then I am so many standard deviations under the mean. This is how we find a z-score. I take my value I want to standardize, subtract the mean, and I divide by the standard deviation. In this example, notice we have women have a mean height of 64.5 inches with a standard deviation of 2.5 inches. If I want to find the standardized height for a value of 68 inches, notice we have a few key items. We have a mean of 64.5 inches. We have a standard deviation of 2.5 inches. And if I want to find the standardized value of 68 inches, if I know z equals x minus the mean over the standard deviation, our x value is the 68, our mean is the 64.5, and my standard deviation is the 2.5. And I would do some simple computation. When we do our computation, note we have a z-score of 1.4. What this means in context is 68 inches is 1.4 standard deviations above the mean. If we look at the following example, the ACT in 1998 had a mean of 22 and a standard deviation of 3.5. In the same year, the SAT had a mean of 1017 and a standard deviation of 185. Tom took both exams in 1998 and scored a 32 on the ACT and a 416 on the SAT. Which test did he do better on? Well, we can highlight a few key things. Note we have ACT, mean of 22, standard deviation of 3.5. For SAT, notice we have a mean of 1017 and a standard deviation of 185. We also know that Tom scored a 32 on the ACT in 1998 and scored a 416 on the SAT, and I want to find out what test he did better on. So we can set up a z-score for both exams. We're going to have a z-score for ACT. Our x value this time will be 32. Our mean value is 22. And a standard deviation is 3.5. For SAT, note we have a, for SAT, we have an x value of 1416. We have our mean value of 1017 and our standard deviation of 185. When we calculate the z-scores, notice our ACT z-score is 2.86 and our SAT z-score is 2.16. So now I have to compare them. Well, which one is further above the mean? If I want to know which one Tom did better on, I want the value that's further positive away from the mean. And so it looks like ACT is better because his z-score is further from the mean in a positive direction. Remember, a z-score gives us an indication of how unusual a value is because it tells us how far it is from the mean. There is no universal standard. However, if I have a larger z-score, negative or positive, the more unusual it is, the more unlikely it is. If we look at the histogram, we notice it is a very symmetrical shape. Well, a density curve is a model describing a distribution. And if I wanted to know the area underneath this curve, think of it as like 100% area completely shaded in, or one whole. Density curves can be symmetric or they can be skewed. In first semester, we will primarily be looking at symmetrical curves. In second semester, we will be looking at symmetrical and skewed distribution curves. Note to self that density curves, they are symmetric, single peak, and bell-shaped. These describe the normal distribution. So things that we can use a normal distribution curve include examples such as human height, standardized test scores, IQ, engineering reliability, etc. Also note that normal curves are just described by the mean and standard deviation. So if I ever see an n and an ordered pair, note the first coordinate is the mean and the second coordinate is the standard deviation. Remember, the mean is the center and the standard deviation is where the steepness of my curve changes. So note in this first picture, we have kind of a short and squatty curve. That means it has a large standard deviation. And this curve on the right, note we have a tinier standard deviation. The curve is taller and steeper. We like normal curves because they can describe real-life data fairly easily. They give us good approximations, and we are going to use them to make various conclusions. The 68, 95, 99.7 rule is also known as the empirical rule, and it applies to all normal curves. So note in this picture, this middle 0, this just represents the mean, okay? And the 0 means I'm 0 standard deviations away from the mean. If we look at the bottom, 1 standard deviation above the mean, 2 standard deviations above the mean, and 3 standard deviations above the mean. I can go in the reverse order as well. This is 1 standard deviation under the mean, 2 standard deviations under the mean, 3 standard deviations under the mean. I'll go there. Okay. Also note that between -1 and +1, this is 68% of my data. If I look between -2 and +2, this is 95% of my data. And if I look between -3 and 3, this is 99.7% of my data. Here is another detailed picture of the 68, 95, 99.7 rule. Note to self, these are my different standard deviations above and below the mean. And note we have our middle 68% marked, our middle 95% marked, and our middle 99.7% marked. But sometimes questions will ask me, well, what percent of observations are 2 standard deviations above the mean or below the mean? If I were to look here, this middle 68, note it's divided into 2 symmetric halves. If I do half of 68, I know this vertical piece here, right here, this vertical piece is 34%. And that means this vertical piece is 34%. Okay? If I look at the middle 95%, so that would be all of this. Okay? Do you see how the 95% it lays on top of the 68%? Okay, if I take 95 minus 68, we get 27.5, or 27. If I take half of 27, I do end up with 13.5%. So I know this piece is 13.5%, and this piece is 13.5%. Okay. If I were to take the middle 99.7%, that would be all of this. Okay. Do you see how the blue and the green sit on top of the yellow? Well, the only places where there is still yellow remaining when I take those pieces out are here. So if I take the 99.7 minus 95, we get 4.7, and half of 4.7 is 2.35%. Okay. And then we see that we have these little pieces left over together. And if I know this section is 99.7, 100 minus 99.7 is 0.3, and half of 0.3 is 0.15%. Okay. So here's your detailed picture. If we look at this next example, it says the length of human pregnancies from conception to birth varies according to a distribution that is approximately normal with a mean of 266 days and a standard deviation of 16 days. If I want to use the 68, 95, 99.7 rule to answer the following questions. Letter A is going to ask you to draw the normal distribution curve. So I'm going to start off with the curve, and I'm going to put my mean directly in the middle. Okay. Now, I know I need to have 3 standard deviations above the mean and 3 standard deviations below the mean. But now I have to ask myself, well, how do I get 1 standard deviation above the mean? Well, I'm going to use my standard deviation, and I'm going to add it to my mean to get 1 standard deviation above the mean. Okay, so I'm thinking in my brain to get this value, I'm going to take my mean plus my standard deviation. Okay, so this value is 282. And I'm going to continue adding 16 to get 2 standard deviations above the mean, 298. And 298 plus 16 is 314. To get underneath the mean, we're going to subtract from the mean. So 266 minus 16 is 250. 250 minus 16 is 234. 234 minus 16 is 218. Okay, so now I'm going to mark my middle 68%, my middle 95%, and the middle 99.7%. This is the bare minimum I need to see on any assessment if it asks you to use the 68, 95, 99.7 rule. So now my next question says, between what values do the lengths of the middle 95% of pregnancies lie? So I'm going to find the middle 95% and note it's between these values. Right, and I'm going to look directly down. So note I'm at 234 and 298. So my answer would be 234 to 298 days. Remember, on the AP exam, they will probably want you to write it in context. So you would have to say the middle 95% of all pregnancies fall between 234 and 298 days. In this next question, we want to know how short are the shortest 2.5% of all pregnancies. This one is a little bit more complex. Now, we know that the middle 95% is here. So I have to ask myself, well, what percent is left over? So for these two halves, together that has to be 5. So if I wanted half of 5 and I want to find shortest 2.5%, would be here. Okay, because this would be 2.5% and this would be 2.5%. And if I want the shortest, I want this data right here. So we're going to say 234 days or less. Okay, and remember, you're probably going to have to write this in context. So you would say the shortest 2.5% of pregnancies are fewer, or 234 days or less. Now, the other way we could have done this problem is we could have written down their vertical percentages from the previous, before we got to the example. Okay, so this would be 34, this is 13.5, this is 2.35, and this is 0.15%. And if I add these two, 2.35 plus 0.15 still gives me 2.5%, and I still get 234 days or less. Here's your assignment and your humor today.